Thank you. I appreciate the SEG Society for putting on this lecture. The SEG invites you to become a member, and more information is available down here at this website. This free lecture is made possible by funding from the SEG, the SEG Foundation, PGS, and land seismic noise specialists. We can produce amazing images and quantitative reservoir analysis with marine seismic data, but often we can't have the same success with land seismic data. And the problem is the additional noise with land seismic data. The noise is a core problem with land seismic data, and it is not well understood. I hope to explain this noise, and this explanation shows that there are long-term and short-term opportunities to improve land seismic quality and reducing costs. About 70% of the world's oil production is on land, and as you can see, the ratio is increasing. Yet, land seismic data often gets less attention than marine seismic data. And we see this in many ways, such as R&D budgets and the focus of technical presentations. And there are many reasons for this, including market forces. But one reason is that land seismic data often doesn't give as much information as marine data because it is noisier and less predictable. Another interesting thing is that land seismic volumes used to be much smaller than marine data, but that is now changing. Land seismic data volumes are going up significantly. Now, back in 2006, Dave Monk predicted channel counts would double every 3.5 years, and that's been surprisingly accurate. So 2006 is about here, and the last 3 data points are new since Dave's prediction. Now notice the last dot here. This last dot is a just recently announced, it's a planned 1.2 million channel survey for 2025. Now this increase in data density certainly helps land seismic data quality and the images, but it doesn't solve the noise problem. The big hammer approach is reaching its limit and it is expensive. Smarter acquisition is also part of the solution. Here we compare a marine shot gatherer with a land shot gatherer. On the marine shot gatherer, you can see there's a lot of clear reflection signal up and down the section. Now on the land shot gatherer, we see a lot of coherent energy, but actually all of this is noise. And these are all refraction multiples. These are an echo of the top P refraction, and this down here is actually an S refraction. None of this energy here is reflection signal. And you can see that here in this talk, I'm focusing on shot-generated noise. You also see that in the noise here that has some coherency and some incoherency. And the combination of that is interesting and makes things difficult. But overall, the difference between marine and land seismic data is like night and day. Here is a sample marine seismic image after migration. You can see a lot of subtle features here can be well resolved. There's a lot of structure in some of these horizons, and there's some faults that you can see, but overall the image is sharp, broadband, truncations and steep dips are well defined, and subtle reflections are resolved. Here's an interesting seismic line that starts in marine and then moves on land and into different surface geologic provinces. And I thank Mike Yates for publishing this work. Now, the quality is pretty good over here on the marine side, but then as you move on land, the signal quality changes dramatically. In some areas, it's actually quite bad. So overall, compared to marine imaging, this is narrow band, has poor truncations, poor steep dips, and I would say the geology down here is not all that clear. Note especially the very poor imaging in the tidal area here and in the hills here. So it's important to point out that land seismic data and noise types actually vary dramatically. And what works in one area may not work well in another area. So be careful about inferring too much from one example. In this talk, I'm going to focus more on the worst types of data. And that's where the noise is easier to see. Even if you think you have good data, realize that the near and far offsets and the very low and the very high frequencies may not be good. And these edge parts of the data are actually vitally important for AVO, impedance inversion, and other forms of quantitative interpretation. So we're always trying to do more with the data, and it's the noise that's blocking us. So I'm hoping I can help all types of data. Why is land seismic noise so difficult? Well, much energy from the initial P wave is converted to other energy in the very near surface, often the top 50 meters, and often it's even less than that. Now, this other energy is often surface waves, not necessarily. It can be other things too. Then much of this other energy is converted back to P waves, essentially with secondary virtual sources. And then it travels deep and becomes corrupted refractions and reflections. This second item is not appreciated that much, and the coherency of the noise is what makes it so difficult and makes it difficult to remove. So I'm going to go into depth on this second item later. The ratio of corrupted coherent noise to remaining initial P wave energy can actually be incredibly high, often 20 and even a factor of 200. And 200 is not an exaggeration. This is why we sometimes need 10,000-fold or more to get a good image. And here's an example of what the very near surface can do to data. And what we're going to do is compare receivers at surface with those buried 9 meters deep. Now in this case, 9 meters is deep enough to get below the problem layer, the weathering layer. And usually the distortion layer is thicker, but in this case, it's 9 meters deep. So the receivers are 9 meters deep and the sources are 9 meters deep. And you can see you get some pretty good clean reflections here. You do have the surface waves, but they're kind of only affecting of the data. Now, if we keep the sources at depth, then put receivers at the surface, you can see through that extra 9 meters, the signal quality suddenly gets really bad. The reflections are strongly distorted, and this distortion is more than static. You also see this faster energy here. It looks like a surface wave, but I believe this is actually a shear refraction. It doesn't appear to be dispersive. This is from Peter Carey et al. Down here. Here's another interesting example, and this comes from Ian Jones. We're looking at a deep geophone response to different source depths. And the sources start at 200 feet and then go shallower. Things are fairly consistent from 200 feet down to 100, but then at 50 feet, the wavelet changes significantly. And then at 5 feet depth, you can see that very little energy is transmitting down deep. So let's focus on these bottom two traces some more and do a trace by trace scaling. And you can see that the source at 5 feet depth has a dramatically different wavelength than 50 feet, which itself is different than that deeper at 100 and 200 feet. Now, in other surface geology areas, this wavelet inconsistency is actually worse. And also, vibrators are often worse too. So you can see that the very near surface is having a big impact on the seismic data. Let me go into more detail now on why land seismic noise is so difficult. And I'm expanding here on my previous explanation. So first, ultra-slow surface velocities can cause very short wavelengths on the order of 2 to 20 meters. Then you have strong conversion of P source to shear energy and surface waves. This is the other energy that I described before. Now, very little energy remains as primary P reflection energy. It's kind of amazing how strong this conversion is. Then you have strong leaking and conversion of this S energy and surface waves back into P noise. And there are several processes that cause this: layering, undulations, and scattering. And in the past, this process has been called guided waves, which I don't like. I'll discuss that more. And the actual details don't matter that much. But the big thing is the fact that it happens, and there are different ways that it can happen. But this leaking and conversion is crucial. And I'll be spending more time on this. Also, you have the fact that near surface is messy at scales of 2 to 20 meters, and that helps this leaking and conversion. Then much of this P noise becomes corrupted refractions and reflections. And this is, of course, very coherent noise. And then there is a multiplicative effect at the source and the receiver. So if you have a factor of 10 at the source and a factor of 10 at the receivers, then you get a factor of 100. And then all these processes work together to produce the strong noise. Now, I'm not the first to really show all these processes. This has been discussed before, but I think I'm putting this all together to show how they work in unison to create strong land seismic noise. And this has some interesting implications. There are several immediate implications from understanding the noise. First, shot and receiver noise will likely correlate well with low surface S velocity. And there are several ways to estimate the surface S velocity, such as soil maps or LiDAR. And this helps you predict the noise and place shots and receivers in possibly much less noisy areas. Two, reducing shear generation at the source will improve data. This is why explosives improve the data, but I think there are other ways of doing this too. Three, reducing shear sensitivity at the receiver will improve the data. I think this is one reason why old arrays would work well. And I'll show you at the end that you can actually produce a better digital array using this concept of reducing shear sensitivity. And finally, distortion of signal is actually a major source of noise. Noise is not only unwanted energy, but it's also distortion of signal. And this has been called poor coupling in the past. And the interesting thing here is if you can undo the distortion, you can recover more signal. And I'll show you an example of that later. The trade-offs in cost and signal to noise is not simple. Now, the contribution of a trace to the final image goes by this formula, basically signal over the amount of total energy in the trace squared, but it's the square that's important. So if you have little signal in your data, the contribution of that trace to the final image goes down dramatically. I'll show you later that if you can reduce noise at the source and the receiver from 80% down to 50%, so this might seem like a moderate reduction, but then the contribution of the trace goes up by a factor of 40. So if reducing this noise costs 10 times more, I would claim it's even worth it because the actual final image will be better. And that's something you can actually easily work out. Your other option, of course, is to just record 40 times more data. So this is where I think being smart can help you optimize the cost and quality of your data. Here's the slide I showed you earlier on the reasons for land seismic noise being so difficult. There are 5 items, and I'm going to go through each one of these now individually. First, ultra slow surface velocities cause short wavelengths of 2 to 20 meters. And this is actually well known and well documented in many areas for unconsolidated sediments. And how slow? Well, shear velocities can go down to 100 meters per second or even less. And this causes strong noise. It's interesting how much the shear velocities can cause P noise, but that's what happens. This is documented for many different things. MASW is a surface wave technique for resolving the shear velocity. There's actually a lot of earthquake risk assessment maps. It turns out the shear velocity is a key estimate for the strength of the ground shaking. And the very low P velocities, and this is of course what causes statics. So if you have strong statics, then you probably have low velocities and also some strong heterogeneity. And here's an example of a certainly very localized low shear modulus. The vibrator was moving along, and then all of a sudden in the field, it sank down because the shear strength wasn't strong enough to support the vibrator. The second item is the strong conversion of a P source into shear energy and surface waves, such that very little energy remains as primary P reflection energy. And this is also well documented. Here's a figure from the paper by Jim Geyser that actually works out the calculations for a simplified near surface. And a high VPVS ratio causes 90 to 95% of vibrator energy to go into shear waves and surface waves. Also, scattering causes P energy to be converted to S energy, and this may be a cause for why dynamite can be very noisy. In heterogeneous area, this is what will happen. And an interesting thing is at the receiver, the conjugate happens. So a vertical receiver can actually be very sensitive to shear energy when the VPVS ratio is high. Here's an example of how much of the source energy goes into surface waves. And this is an explosive source, I might add, even at depth. You see these traces on the inner offsets that are just incredibly strong. These traces are actually clipped by a factor of 10 or more. And this shows that 95% or more of source energy can go into this other energy that I called it before. Now, in this case, the surface waves stay localized, and you can work with the weaker reflection energy that you see over here. But what if this strong surface wave energy leaks out? Now let's get into the third item, which is a key item and kind of the meat of this talk. And that's the strong conversion of shear energy and surface waves into P noise. And that's caused by layering, undulations, and scattering. This is the leaking effect. So here you have a near surface, and this can have a thickness of 3 to 30 meters. And this initially traps a lot of energy, such as surface waves, but you have heterogeneities in this layer. You also have undulations at the boundary going up and down, and you'll have layering. And all of these things serve to convert the surface waves into P noise. So the strong initial surface waves might propagate only a few hundred meters and then are converted to deeper traveling reflection and refraction noise energy. Layering is one process that can cause surface waves to leak. And here's a nice figure from Andrew Bakulin. And it shows you have very strong surface waves, but they're leaking out into this faster energy that's overlaying the reflections. This type of leaking is sometimes called guided waves. I don't really like that term. I like to call these refraction multiples, and that'll be clearer in the next slide. They're really not quite guided waves, and they're caused by other things, and I just think refraction multiples is more descriptive. Here I show how scattering can convert the surface waves into refraction multiples. This is the previous example I showed you with the leaking surface waves here. And here, notice that the actual surface wave is right here. It's very weak, pointed to by the arrow. It's very slow velocity on the near offsets. It's so weak because most of the energy has been leaked out into these refraction multiples. And now you can see why I call them refraction multiples, because they really are echoes of the refractions. These are the P refraction multiples, and down here are the S refraction multiples. And notice that they're actually stronger than the P refraction multiples. And they have some irregularities so that a radon velocity filter won't easily remove them. So this is strong energy with irregularity, and it arrives at the same time as the reflections. And the S refraction multiples are surprisingly strong. Here's a nice movie example of three-dimensional scattering being caused by sand dunes. You can see the sand dune here. So we're kind of looking at an oblique view, and we're going to set off a source on the surface. Here's the source, and you can see the sand dune traps a lot of energy and is ringing, and the sand dune acts as a secondary source that actually lasts for quite a long time, sending out a lot of corrupt and coherent energy as a secondary source. This nice example came from this reference here. Here is a 2D wave field movie. First I'll show with no scattering, and then we'll move into the more interesting cases. Start off with the source here. You can see a nice clean wave front. It's expanding out, see the very clear reflections. You can see the very strong surface energy here in the very near surface, but it's not scattered. It's trapped in the near surface, and it's fairly slow. And notice also that the deep wave field here is not corrupted. Overall, the wave field is pretty simple. Now let's look at a more complex case. Here's the wave field movie with scattering. Now, before I run this, here is the velocity model for the very near surface. You have a slow velocity layer, and notice that it has some heterogeneities. And the second layer also has a few weak heterogeneities. But after that, after about 30 meters, everything is uniform. So here you can see the movie start. And notice all this energy at later times. There's no clean initial wave fields. This is deep noise energy, and it comes from leaking energy out of the near surface waveguide in the very near surface. And the energy is really strong compared to the initial P source. I compare the wave field snapshots for the two movies. On the top is with no surface scattering. You can see there's not much junk energy in the middle, and you have a nice clean early or initial P arrival. But with surface scattering, the ratio of this later junk energy to the direct P arrival, the ratio is strong, and the direct P arrival is actually very weak. Now you might ask, where did all this energy come from? Well, it came from radiation out of the near surface, and all that energy is up here. So it's in there, it's just going very slow and it's very localized. But down here with scattering, it's radiated out. You see how strong it is, and it becomes later coherent reflections and refractions. Here's another example, and this time, instead of having surface scattering, we have just gentle undulations of the top surface layer. Now there is a strong velocity contrast between these upper layers. Surface waves are very sensitive, so if you make very sensitive to having very nice flat waveguide, so the undulations cause some significant issues, cause significant scattering, and here you see that scattering. It's almost as bad as if you had um, in the near surface. So it doesn't take much for strong surface waves to leak out. It can be scattering, it can be gentle surface undulations, or it can be layering. And again, this deep noise is the problem. The initial P wavefront is here. It's very weak compared to this later noise. So much of the P noise is actually corrupted reflections and refractions. And the problem is that this is very coherent noise. Here are two examples of real data, Papua New Guinea and West Texas. And all this energy that you see on the shot gather is this corrupted noise. Most of it is refraction noise. You can see a little bit of the surface wave here. Again, it's weak because it's all been scattered. This is the S refraction multiples, and this is all the P refraction multiples. And from West Texas, you can see the S refraction multiples here, very strong, and P refraction multiples. Here I'll show the problem of the reflection and refraction noise using the Ragone modeling trick. What we do, and what that trick is first you model the data with the full model, and you see all the noisy data here. And then you model again using only the surface model and no reflectors down deep. And this is what you have here. So we're only modeling maybe the top 300 meters or so. And then you subtract the two. So you're subtracting out all the surface traveling energy. And this is the results after subtraction. And since this is synthetic modeling, you can see the subtraction has been nearly perfect. And you have a lot of reflections here. Statics works very well on them, and that'll very easily clean up and make these reflections smooth. But what you'll see later is actually that these reflections are in the wrong place, that there is a lot of noise in here, and the image is fairly imperfect. And this shows that a big problem is really corrupted reflection and refraction noise. Here is the image, the migration image of the elastic data using the Ragone trick. And if we had been able to subtract all the surface noise out, this image would be perfect. And you can kind of see a faint echo of what the image should look like. You see these trapezoids down here, and yeah, and you see the reflector down here with some bumps, but there's a lot of noise in here. And the shallow part of the model and the image is pretty good, but the corrupted reflection energy is a big problem. Here is the same acoustic energy, or the same migration with acoustic energy using the Ragone trick. And now you can see the image is pretty darn good. The reflections are slightly different place and they're skewed in the different direction, but you get this idea of the style of what the image should look like. And finally, there is a multiplicative effect at the source and the receiver. So far in my modeling, I've shown you the effect of scattering and leaking at the source, but this effect also happens at the receiver. And this is where if you only have 0.1 energy remaining at the source and 0.1 energy remaining at the receiver, then you have actually 1/100th of signal energy remaining in the final trace. So let me run this model. Here you see a source at depth with a clean wave field going up. And what do you expect to happen? Well, you do get a reflection, but see all the scattering? The scattering has actually trapped coming energy in the near surface. And you now have very strong energy in the near surface, and you have a lot of ringing. So effectively, you get a very complicated receiver function. And then this is kind of the conjugate of what happens at the source. So this multiplicative effect at the source and the receiver. So if at the source, 90% of the energy is converted to noise, 10% remains as signal. At the receiver, the same thing happens. Combining source and receiver, 10% times 10% means remaining signal is 1%. So things go bad fast. Surface conditions can have a big impact. Now let me show you how the near surface can be very messy at scales of 2 to 20 meters. This shows you how weathering can start to break up rock and create boulders. So you can have soft sediment next to boulders, which creates some actually incredibly strong scattering and heterogeneity. But the bottom of your weathering layer can be a boulder jumble. And actually, here's a road cut where you see that. You see all these boulders. You also have tree roots. Those are very significant, different than soil. You have undulations. You have a lot of little things happening here. Here's another nice example. This is a satellite view, and what you can see, this is a meandering stream bed that over time has, well, created these channels in different locations. And this river is probably 20 or 40 meters wide. So that creates a lot of heterogeneities, and deserts, even deserts can be heterogeneous. In fact, we know the Middle East is one of the noisier places. So when you go out and you're in the fields, make a note of the amount of heterogeneity that you see. Now I want to walk you through some interesting calculations on how surface noise corresponds to the value of a trace. And I said before that if surface noise goes from 50% to 80% at the source and receiver, the value of the trace goes down by 40x. So let's say we have 50% of energy converted to noise at the source and at the receiver. That means the trace has 0.25 signal remaining, and the value of the trace, its contribution to the final image, is the square of that. So that comes out to 0.0625. And this means kind of a stack of 16 traces will produce a pretty good result. But now if 80% of the energy is converted to noise at the source and receiver, the trace has 0.04 signal remaining, and the value is 0.0016. And then you need about 625 traces for pretty good results, and that's about 40 times more than 16. So the value of a trace really goes by the surface noise to the fourth power. That's a strong power. Or another way, reducing surface noise, if you're in a noisy area, reducing surface noise from 0.9 to 0.8 fraction, which may appear like a small improvement, but that actually increases the value of the traces by a factor of 16. This is a big effect. So using what we've learned about the causes of surface noise, I want to show you how we can use this to improve the data. And here are examples of using surface distortion correction. These are advanced surface distortion corrections. You can think of them a little bit like surface consistent decon, but on steroids. And the top is a pre-stack gathers, and these are tightly spaced traces. And we're applying a method called wave equation refraction statics. Statics have already been applied, and you can see that it's improving the early arrivals, but it's also improving the deeper part. You can see there's much more coherent reflection energy down deeper. And then post-stack, using FWC surface corrections, without the surface scattering corrections, we get this image. And then with the surface scattering corrections, we get this image. And you can see a significant improvement. Here's an example of using this noise insight to improve acquisition. Now we know old analog arrays can help improve data quality over point receivers. So here I created an optimized phased array and compared it with a simple array sum. And you see that here. On the left is a point receiver gather. It's a fairly noisy data. In the middle is a simple array sum, and that's where we just stack all 6 items in the array, all 6 receivers in the array. And on the right is an optimized phased array where we do a smart sum with corrections. So the optimized phased array actually combines each digital fashion with corrections in an optimal fashion to reduce the shear sensitivity. And you can see it's done a pretty good job. In the red circles, you can now see some significant signal, which you didn't really see before. Now, I didn't have a good test data set for this, so I just used the Netherlands scan data set, and that had the benefit of having 5-meter receiver spacing. So I was able to create 30-meter arrays by just grouping 6 receivers. So here I've removed the point receiver gather on the left, and then moved the two previous displays to the left, and then I've added a difference display here on the right. And you can see that the optimized phased array has significantly taken out refraction multiples. So the benefit of this array is that it can reduce noise by a factor of n instead of square root of n. And this is where n is the number of receivers in the array. The trick here is doing the optimization early in the processing flow so that this then helps later processing. So in summary, the thin near surface of the Earth produces 100 times more noise, can produce 100 times more noise on land seismic data than on marine by having ultra slow surface velocities that cause short wavelengths, and the near surface is messy at that scale. Then you get strong conversion of the P source to S and surface waves. And that then converts a second time back to P noise. And that second conversion is a problem. It's caused by layering, undulations, and scattering. And very little original energy remains as primary P reflection energy. And vertical receivers, as well as vertical sources, are very sensitive to the S energy for high VPVS ratios. And then we create corrupted reflections and refractions, which is very coherent noise. And then we have the multiplicative effect at the source and at the receiver. The general implications for noisy areas are give up hope that sampling the whole noise wave field will solve your problem. There is little benefit to ultra-dense inline receiver spacing. Better use of high channel counts may be irregular layout or creating digital arrays. 2D tight digital arrays and novel sources have potential. Small changes in surface conditions can produce strong 4D noise, and that's important for CCUS. FWI has limited benefit in solving the surface noise within 15 years, I believe. And there are trade-offs. The trade-offs between cost and signal to noise are not simple. Signal to noise, or the value of a trace, can go by the fourth power of the surface noise. And specialized testing and modeling of the noise in an area can be helpful. Finally, I want to mention that I think the key takeaway is that there is opportunity to improve the quality and cost of land seismic acquisition beyond just collecting more data faster. And I want to leave you with a question: how much research as an industry are we really doing, and who is doing it? Thank you very much.